Hi, welcome back. Today we're going to be looking at something called implicit differentiation. This is how we take the derivative of equations that we cannot define as a function, or we just can't solve that as a function, and we just don't want to. It is very important to note today that many of our derivatives will be defined in both terms of x and y. So let's take a look at an example right here. We have this equation x squared y minus yx squared equals 3. And this is the graph. Now, obviously, when we look at this, this will not be a function because it's going to fail that vertical line test in many different parts. So, some things we might want to think about as we go through today. What if we wanted to find the slope of the graph at x equals 5? Now, notice, because it's not a function, we can get multiple answers. And so, in most cases, we want to find the slope at a point, we only get one answer. But because these are not functions, we can get two or more answers. In this case, just two. We'll see an example like that tomorrow. What about horizontal and vertical tangents? Are there any horizontal? Remember, for horizontal, we say the slope is 0. That's our critical number. And for vertical, we say that the slope is undefined or just does not exist. Yeah, and we look here, we can see them. Yeah, look over here. Here we have a slope is 0. And over here, we have somewhere where the slope does not exist, a vertical tangent. So the question we want to ask is, well, how can we find out where those occur? And we're going to talk about that today and tomorrow, mainly tomorrow. And then the last one is, what's happening to the slope as x goes to infinity? Well, it's kind of weird. As x goes to 0, gave away the answer. It kind of looks like as we go to 0, the slope here starts to grow without bounds above the x-axis, but decreases without bounds below the x-axis. So we got some things to really think about as we go through today. Now, to answer these and more, we're going to use a technique called implicit differentiation. There are two main types of relationships when we talk about equations, and they're the following. We have explicit relationships. These are functions that can be solved for. In other words, I can say y is equal to x minus 3. Y is equal to 4 root x plus x squared. Area is pi r squared. I can solve for a variable. I have a variable explicitly solved for. The other one we're going to talk about today, implicit. These are variables that we cannot solve for or not solve, or that are just not solved. For example, we have this y cubed plus y squared minus x squared minus 4. We cannot here solve for explicitly for y. It just can't be done. Now the next one, x plus y is 4. Yeah, I could put this into the other column if we solve for y. So some implicits can be explicit if we can solve for y. And then of course we can get tricky with it. We got the sine x sine y equals root 3 over 4. And if you notice, we're always going to have these x's and our y's here. So let's get started. To take these derivatives, we are going to use Leibniz's notation. We really like Leibniz because it's going to give us a way that we can relate x independently from y. So it makes it much easier for us when we think of dy dx. So when we take these derivatives, we're going to be taking the derivative of x we're going to be taking the derivative of y with respect to x. And that's what this Leibniz notation tells us right here. This is saying we are going to take the derivative of the function y with respect to x. Now, when we get to related rates, we're going to change this variable. So today's lesson is very important for us. We really want to pay attention. So let's take a look at a very simple one. This is an explicit function. And of course, we know the answer, the derivative of y equals 3x squared is just going to be 6x. But let's take a look at this another way. Let's do this what we call implicitly. When we think implicit, we always want to think chain rule. There's always an inside. And what do I mean by that? I could write this as y equals 3 times x squared. So now I have an inside. So when I take my derivative, the derivative of y is just dy dx. But when I take the derivative here, I'm thinking chain rule. I drop my 2, I get 6, x to the first, And then what's the derivative of the inside? Well, that's just 1. But where does that 1 come from? Well, I'm taking the derivative with respect to x. So if I take the derivative of this with respect to x, we're just going to get dx, the change in x, which is just 1. We just don't ever write that. Well, no, that's a 2. Somebody corrects me. That should be a 6. Sorry, 2 times 3 is 6. And again, if you notice, we do get the 6x that we said it would be. Sorry about that. I forgot to multiply by my 3. So we don't ever write it this way because one takes too long, because the derivative of x with respect to x is just going to be 1. So we never write it that way. So let's take a look at how we solve these problems. And we're going to zoom in a little bit here. So for question number 2, we got this function, y cubed plus y squared minus x squared equals negative 4. When we take the derivative, this is what we're going to do. We are going to think chain rule. Everything is in parentheses that has a y on it. We're not going to worry so much about the x. We'll talk about that in a second. When we take the derivative, we are going to get 3y squared, just like a normal derivative. But I have a chain rule. I take the derivative of y, and that's going to give me dy dx, my chain rule. I'll show you a really cool example in just a second how this really works, what's really going on here. Plus, when we take the derivative here, we're going to get 2y to the first, and then my chain rule, dy dx. Minus, when we take the derivative of x, we're just going to get 2x. We're going to multiply it by 1 because the derivative of x is just 1. So we just never really worry about that. Over here, that just becomes 0. 0 because 4 is just a constant. Next, anything that has a dy dx will stay. Everything else goes. So I'm going to keep everything with a dy dx. 3y squared dy dx plus 2y dy dx. And I'm going to bring this 2x over. And then we do a little bit of algebra. I can factor out a dy dx here. And that's going to give us 3y squared plus 2y equals 2x. And now I can divide. Therefore, my derivative, we would get 2x over 3y squared plus 2y. And there's our derivative. This is actually quite an easy unit. Most people do really well on this unit. And we're going to take a look at some shortcuts too. But before we do that, I want to show you something real fast. Okay? I'm going to put this on a little sticky here. There we go. Whoop, that may not work. There we go. I'm going to put this on a sticky right here. We know from Algebra 1 that y is f of x. So if I have something like y cubed plus y squared minus x squared equals negative 4, I can replace that with f of x. And if you notice, it's the exact same problem we just did. But now we can actually see the chain rule. This is going to give us 3 f of x squared. And of course that's going to be squared. And our chain rule is going to be this f prime of x. So we did the same thing here. 3y squared times f prime of x, or dy dx. It's just a nicer notation versus using all of these little f's here. Okay? So, all right, so let's take a look at the next example here. So here's my hint. This is the thing I want to tell you. Most people will forget that we're actually doing a chain rule right here. So here's the hint. Anytime you take the derivative of a y, you just multiply by dy dx. So if you take the derivative of y, we're just going to multiply by dy dx. That's almost anybody remembers. Okay? We just multiply by dy dx. But where is it coming from, in case you ever ask this on Jeopardy? That's our chain rule. It comes from our chain rule. So let's apply it. Let's take a look at number 3 here, where we have this x to the 4th, y to the 4th, plus y equals x. Be careful. Here we are actually going to use our product rule. So if you forgot the product rule, it's f g prime plus g f prime. So when we take our derivative, we're going to get the first, which is x to the fourth, times the derivative of the second. This is where I need to do my chain rule. I'm going to get 4y cubed, but my rule says if I take the derivative of a y, I multiply by dy dx. So I'm going to multiply this by dy dx. Plus the second, which is my y to the fourth, times the derivative of x to the fourth, which is just 4x cubed. Plus, I'm taking the derivative of a y, that's dy dx, and this time it's just going to equal 1. The derivative of x is just 1. Anything that has a dy dx will stay. Everything else goes. Now, I can shorten this a lot. Notice I have two terms with a dy dx. I know I'm going to factor that out. So I can go and do that. And this just becomes 4x to the fourth y cubed plus, be careful, there is a 1 in front of there, so plus 1 equals 1 minus, I'm going to bring all this over, 4x cubed y to the fourth. And now I can just solve. There we go. Shortcut the algebra, not the calculus. 1 minus 4x cubed y to the fourth over 4x to the fourth y cubed plus 1. And there's our derivative. Very easy to do. Let's take a look at example number 4. I'm going to slide on over. Oh no. Oh no. A product rule. So we're going to see these product rules a lot, but I'm going to show you something here that will help you out in the future. When we take the derivative, x squared, that's just our 2x. But when I do product rule, I tend to use brackets. We'll see why in a second here. Number 6. When we do our product rule, the first times the derivative of the second, which is just our dy dx, plus the second times the derivative of the first. That's my product rule. Minus, now I got to take the derivative of y squared. But again, this is our implicit. This is our chain rule. We're going to get 2y, but then I got to multiply by the derivative of that y, which is dy dx. Remember, if I take the derivative of a y, always multiply by dy dx. And this is just going to equal 0. Distribute, just a 1 I'm distributing, so it doesn't really change anything, plus x dy dx plus y minus 2y dy dx equal to 0. And our rule, anything with a dy dx will stay. Everything else has to go. I'm going to box those, okay? So they both have a dy dx. I'm going to write that out. dy dx. And I'm factoring it out. So that's going to leave me, if I factor out the dy dx here, I'm left with x minus 2y. And what's that can equal? Well, I just bring these two over. Negative y minus 2x. I'm just bringing those over, right? And I get dy dx equaling negative y minus 2x over x minus 2y. And there's our derivative. All right, we're going to pause this video, stop this video here, go on to video number 2. We'll take a look at a few more examples. I'll see you then.